All right, so let's just finish up with the program that we almost completed last Friday, where we were reading in a decibel level from the user, and we were outputting, what level it is, right? And so we started off with asking whether or not it was between 0 and 60, right? We also decided, well, what happens when it's negative? We'll decide that that's an error, and so we'll echo an error message here and then quit with a different type of error message. Otherwise, we've got quiet, conversational, loud. Oops, I don't have it. That's the next one. What happens if it's 195 or more, though? So the decibel level here. Let's go ahead and execute this and provide a command line argument. Just say 200 or so, 200 decibels. It doesn't output anything, and that's because we have an if, else, but we don't have an else condition. Remember that that's completely optional. But in this case, it affects our program if we don't have it, because if it's anything other than what we've already defined, what should we do here? Let's have a catch-all. Remember that this is the most general case here. Else, what should I print in this case? Right? We never really defined it, right? So it is undefined. I'll just go ahead and do that. Again, if you're a real program, you would go back to stakeholders, the people that are responsible for paying for or ordering this program, and then you'd ask them, well, what should happen at 195 and above? And if they say, I don't know, well, then this is good enough, right? So let's go ahead and see again that it is now undefined. I will make sure that you have this in your notes. Let me go ahead and move this over to decibel.c so that we can reuse this demo program here to get it on to the next topic. Right? And the next topic is loops. So whereas conditions give you a decision, do A or don't do A, or do A or do B, or do A or C, or B or C or D, or make branches basically of I'm going to go that way or I'm going to go that way. Loops allow you to repeat the same code over and over again, so that you don't have to write the code and then write it, copy paste it to run it a second time, copy paste it to run it a third time, etc. Don't do that, right? You write a loop instead. There are 4 basic elements to loop control structures. The first one is, well, if you're running around a track, right? Well, you have to start somewhere, and that's an initialization. There's an initialization statement that says where the loop starts, because you always have to have a starting point. Then you have a continuation condition. How long should you keep running around this track, right? So I get done with my first lap around the track, and I ask, should I keep going? Well, you have 5 more laps to go, so the answer is yes. All right, keep going, and keep going until some termination condition is met. Now, the continuation condition and the termination condition are the exact same thing. They're just complements of each other, right? A continuation condition means, yes, you keep going. A termination condition is the negative of that, says, no, stop, and don't go any further. There's an increment or update statement that makes progress towards that terminating condition. If you don't have that and you just keep running around the track and you never stop, right? You're going to run around the track infinitely, forever. So you need to make progress towards that termination condition at some point, right? Otherwise, you have what's called an infinite loop. Then finally, you have the loop body, right? You have to actually be doing something. In our case, we're running around the track. And this is executed with every iteration of the loop. Okay. So let's go ahead and take a look at the first loop that we're going to introduce. There are a couple of loops, the for loop and a while loop that we'll cover. But the for loop is called a for loop because guess what? It uses the keyword for, right? All three of the main elements, the initialization, the continuation, and the increment, are all on the same line. Okay. So let's come over here to our demo and let's write our first for loop. For int I equals 0. This is my initialization condition, right? I'm going to start at I being 0. I'm going to initialize I to 0. While I is less than 10, right? We will continue going. This is the continuation condition. While I is strictly less than 10, I execute this loop at least one more time. And then I'm going to make progress towards my termination condition, and this is new syntax, right? I++. We'll cover this in detail in a second, but for now, just know that it adds 1 to I. So if I starts at 0, then you add 1 to it. Now it's 1, 2, 3, 4. It's a counting loop, basically. And let's go ahead and print out the values of I that we're actually running over here. %d and the line I. Right. Now let me go ahead and GCC this again. Oops. GCC. Come on. GCC. All right. And let's run this. But before I run this, help me to predict what numbers are going to be printed. What's the first number that gets printed? 0, because that's where we start. Then this increment condition says, okay, add 1 to it. So 1, and then it gets printed again. Right? Add 2, it gets printed again. 3, 4, 5, 6, 7, 8. 8 is less than 10, right? So it gets printed. Then, at the end of the loop, we increment 1 once more. So now we're up to 9. Is 9 strictly less than 10? Yep. So what gets printed? 9. Now, on the next iteration, it's going to say I is now going to be 10. Is 10 strictly less than 10? Nope. As a consequence, we jump out of this loop, and only 0 through 9 are printed. Okay? Now, what I want to do next, before we look at the nuances of this loop, is to actually see it in action. There's this really nice visualization tool called Python Tutor, even though we're not using Python. That's what the website is called. We're actually editing C code here. Now, the only difference is instead of putting 10 here, I put it into a variable up here. That way you can change it if you want to go up to 100, if you only want to go up to, but not including 7, etc., etc. I'm going to go ahead and restore that to 10. Let's visualize this execution, okay? And we'll see how it works step by step. I'm going to step through this one line at a time. N gets initialized to 10. You see it over here, right? I has been created, but it hasn't been initialized yet because we haven't run this I equals 0 yet, right? So it now gets initialized to 0. Now we're on line 7, and what's going to happen? It's going to print the current value, which is 0. Okay. Now, what happens when you come up back up to the top of this loop? I plus plus. It gets incremented. I is now 1, and 1 is still less than 10. I can zoom in if we're having trouble. There we go. All right, there we go. All right, and so it prints out 1, and you can see the printout up here, 0, 1. Next, it gets incremented to 2, right? And 2 gets printed out, and it comes back up to the top of the loop. So 3 gets printed, goes up to 4, 5, 6, 7, 8, 9. Just as we predicted, it's going to print out 8, and then when it comes back up, I is now equal to 9, and it gets printed, and then we jump out of the for loop. And there's nothing left in the program. You can go ahead and use this if you want to visualize your code. We'll use this throughout the semester when I'm demonstrating stuff. But it's pythontutor.com, and then you would, I think if you just go there, it'll have an option for C right here, right? And then you can edit this code, right? And you can put whatever code you want in here, have it visualize it for you, and you can see what it looks like going line by line. This is a nice tool for beginners, but by the middle of the semester, we'll be using a more advanced tool called a debugger. GDB is our debugger of choice for this class, and we'll be doing this stuff from the command line, right? But it's the same basic idea. Okay. All right, so there is our first loop. In fact, this is what's called an idiomatic for loop, right? It is, remember those idioms, things that are just part of the language that have no literal meaning but have an understood metaphorical meaning, right? You're going to be writing this loop so many times in your lives, this type of loop, so many times in your life that you're just going to do it by rote. Starting at 0, going up to, but not including n, because you're going to iterate over elements in an array to process data, right? So once again, the initialization statement, let me write, oops, it's starting at 0, right? Starts I at the value 0, right? The continuation condition is I is less than n, right? Is checked at the start of the loop, right? If it is true, and I'm not going to put that into code, I'm just going to say that I use italics there. If it is true, the loop body executes, right? If it is false, the loop body does not execute, and control flow continues after the loop. Right? The program continues after that closing curly bracket there. Okay. The initialization statement is only ever executed once, right, before the start of the loop. The increment statement, in this case it's I++, is executed at the end of each loop, okay? And every time at the end of each loop, right? There is new syntax here, right? That I++ is short for I is equal to I plus 1, right? In other words, it just adds 1 to the variable I. And why do we have this? It's called syntactic sugar, right? Just like you use abbreviations in real life all the time, right? We use abbreviations in code. And just adding 1 to an index variable or a variable called I, it's so common that we have the ultimate shorthand here of I++. Right? There is other syntax that you might see at some point. You can also use the ++, which is the prefix version, but avoid. Right? So Zybooks might cover this, I'm not sure, but there is a subtle difference between the two. And I never remember. I know what the difference is, but I never remember which one is which. So I never bother trying to remember. I only ever use I++, the postfix version of this. But if you want to, go ahead. As long as you're consistent about it. You might be asking yourself, well, if you can add one, can you subtract one? And the answer is yes. I minus minus decrements I by 1. It's equivalent to, or it's kind of like I is equal to I minus 1. And there are other compound assignment operators. Right? For example, you can say I plus equals 2. This is shorthand for I is equal to I plus 2. Right? Plus plus only ever does ones. Right? Adds 1, or minus minus only ever does ones. -1. If you want to go up by 2s, 0, 2, 4, 6, 8, etc. Right? You can do that with 2. And it doesn't have to be 2. It could be 3. It could be 5. It could be an entire expression if you want to. Right? Well, if you've got plus, you've also got minus. Right? That one will go down by 2. Right? You can also do multiplication. Right? So, there we go. I times equals 2. And that'll double it each time. Right? So this doubles it. Right? So if it was 10 before, now it's 20. Right? If it was 2 before, now it's 4. If it were 0 before, what is it now? 0, because 0 times 2 is still 0. Right? You can also do division, but be careful because these are integers. So you have integer truncation. If I go I is equal to I divided by 2, the shorthand for that is I divides equals 2. If it were 10, now it's down to 5. But if it were 7, what is it down to now? It can't be 3.5 because of truncation. So what happens? Now it's just 3. Okay. Some other observations about this code. Right? Let's come up here. What do you see about this code here? I see a semicolon on the initialization condition. I see a semicolon on the continuation condition, but I don't see a semicolon on the increment condition. That's just the syntax, unfortunately. I do think that it is unfortunately inconsistent. You should have a semicolon here, but they just thought, oh, that's not necessary. Let's go ahead and take that off. Because it's acting kind of like not a semicolon, but a comma. So initialization, comma, continuation, comma, then finally increment, and there's no comma after that. But whatever. Semicolons are at the end of the initialization and continuation statement, but not the increment statement. If you tried to do that, then GCC will have a fit here. It has no idea what you're talking about because there should not be a semicolon there. Right? So that's a full syntax error there. Right? All right. So let's come back over here and let's go ahead and rewrite this loop. If I go back 50 years, right, really, really old school C, I actually couldn't even write this. I couldn't have even written this, I think, 35 years ago. Instead, what you would have had to do is you would have had to write it like this. Create the variable I before the for loop. Right? Let me show you the consequences of the good consequences of not doing that. So first of all, what value does I have after this loop is done? right, I. Let me print it one more time here. Now remember, let me go ahead and change this so that it's n, right? Int n is equal to 10. We'll do it that way, okay? Now it prints 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then how do we break out of this for loop here? It prints 9, then it comes up here, 9 plus plus is going to be 10. 10 is not strictly less than 10, so it breaks out of the loop here. So my guess is that I would have a value of 10 because that's how we broke out of the loop. And except that GCC has no idea what you're talking about on that line. On line 20, the declaration of I have no idea what you're talking about. That's what GCC is saying. Why? Because we scoped it. Remember scope? That's the area of the code that you can actually see it because you're looking through a scope and you only see what's in the scope, not things outside of the scope. Well, because we did it this way, it only exists for this for loop. That's a very good thing, right? We're limiting the scope as much as possible. The variable I no longer exists as of line 19. It was born on line 16. It was used for this entirety of this loop, but on line 19, it's gone, right? It's out of scope now. I can change that by declaring it before the scope, or before the loop, excuse me, right? There we go. There's how you would do it in old school C, right? 35 years ago C. And now you can see that after the loop, after the loop, I will be 10, right? Because that's not part of the loop. It goes from 0 to 9 just as before, but after the loop, it has a value of 10, right? So you can scope variables outside the loop, but don't do that, right? Instead, in general, you should limit the scope to the variables as much as possible. This is because you want to avoid what are called side effects, right? If I use I, just one I for every single loop, right? I'm going to use it for that loop and that loop and that loop and that loop. I start to lose myself, right? Did I reset it, right? Is that loop affecting that loop over there, right? Those are the side effects that you want to avoid, right? You want to avoid chaos. By the way, let's go in on that. Is I a good variable name? That's a good question. I'd argue no, not generally, but it's so common to use I, J, and K in your loops that everybody does it, right? It is probably not great, but okay, right? We're not going to dock you for it, certainly, because that's what everybody does, right? Others would include, well, what comes after I? J. What comes after that? K. So if you have a loop within a loop within a loop and you can have that, you would use I, J, and K just because they come after each other. In general, though, we use I. Why did we settle on I? Well, because it stands for an increment or an index variable, and that's why we use I. There's a question. Yeah, go ahead.
Is there going to be an issue if you define I and then redefine it in your loop, or when you redefine it in your loop, does it create a whole new variable even though it's the same?
Good question. So let's do it. Let's do it the new school way, right? Not the 35 years ago C. And now I can't have it after the loop, right? There we go. We'll start I at a 10 and go up to 100, up to and including 100, just to show you can use any less than or equal to here. And I'll go up by factors of 10, plus equals 10. That'll print out 10, 20, 30, 40, all the way up to 100, right? GCC. Now, how many I variables are there? There are actually two. One for the first one that gets born on line 16 and dies on line 18. A second one that gets born on line 20 and then dies on line 22. I wonder what the visualization tool would do with that. Let's try it. Blah, blah, blah. All right, so there's 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? And when we get out of this, I imagine that I dies and goes away. It'll probably disappear. Right? And it becomes question mark again. But it's immediately gets reborn on line 10 and goes 10, 20, 30, 40, 50. Technically, they are different variables. In fact, I don't know if I can do this or not, but if I try to define another I here, int I is equal to 42, right? It actually might be okay with this. Nope, it's not. Well, actually, it is. It is okay. That's just a warning. Now, how many I variables are there? 3. There's one that exists for the entire program. It was born on line 16 and it dies on line 24. And then within this loop, we've got a different I. Right? So how do I access this I? I have no idea. This is why you don't do these things. Right? How to get the I that has a value of 42? Right? You'd have to reference the outer scope somehow, and I'm not sure how to do that off the top of my head. Right? In any case, this is terrible practice. Don't do this. Right? Okay. So, multiple I variables there. Thanks for the warning, though, GCC. Right. All right. There are also while loops. While loops are different in that, well, first of all, they use a different keyword. What do you think they use? The while keyword, exactly. The main difference is that all three of the elements, the initialization, the continuation, and the increment, they're all done on different lines. For this, it gives you a little bit more fine control on how your loops operate. Because with a for loop, the continuation is always checked at the beginning, the increment is always done at the end. But with a while loop, you have a little bit more control on how this operates. So first of all, let me get rid of that bad code. Right, there we go. And let me go ahead and rewrite that for loop, but I'll rewrite it as a while loop. While I is equal or less than 10, right? There we go. I will print it out. All right, so there's the same, or not 10, but n. Sorry, there we go. Come on, there we go. All right, so the continuation condition is bound to the while loop. But do you see the initialization condition? Nope, I don't either. That means it's up to us to do it before the loop. It wouldn't make much sense to have the starting line at the end of the loop, right? That's putting the cart before the horse. So I'll go ahead and create another variable here called I, and I'll initialize it to 0. Right? Now remember that this is probably okay, just with a warning. Not even a warning this time, right? Because we are using it right here. But there are two I's here. There is one that was born on line 17, dies on line 19. There is one that was born on line 20, and then dies at the end of the program on line 25. Okay? I'm saying that it's born and dies because we do say that there's a life cycle to variables. There's a life cycle to a program, right? Because a program has a beginning and an end, right? Just like a variable has the beginning of a scope and an end of a scope. All right, let me go ahead and run this. I already compiled it, so let's run it. First of all, you saw the initialization. It starts at 0. There's the continuation, but I don't see the increment. So let's predict what's going to happen here. I is 0. Is I less than 10? Yep. So it prints. Comes back up to here. Did I change 0? Nope. So is 0 is still less than 10? What's going to happen? 0, 0, 0, 0. Right? Off to infinity. Okay? That's my first infinite loop. You will write an infinite loop many times in your lives. But you need to understand how to get yourself out of this corner, right? I can't type anything, right? I'm mashing my keyboard right now and nothing's happening. I have to kill this program first. To kill it, Control C, all right? So if you've got an infinite loop or a very long run, if I never printed anything, by the way, would it have been apparent that I was in an infinite loop? It just sits there and hangs. Oh, maybe it's just taking a really long time. No, it's in an infinite loop. Let's kill it and rethink what we're doing, right? So you're going to have to kill it with Control C, and I believe that the same is on Windows too. Right? All right. So I need an increment. If I want it to happen just like a for loop, I can do it at the end of the for loop. Right? Let me go ahead and print some nice ASCII text here. There we go. So that we can see the differences between these two loops. Right? So there's 0 through 9. That's the for loop. Here's my while loop, 0 through 9 as well. That's because I did this at the end of the loop. I'm getting the exact same behavior. What if I did it at the beginning of the loop? Yeah, let's look at the Python tutor here and see what it does. Right? The order of operations here, or how it works. Right? So remember, I++ is at the beginning of the loop. So let's go ahead and go next. Right? Now I is 0. Is 0 less than 10? Yes. So it executes. But the first thing it does is it takes that 0 and adds 1 to it. Consequently, what's the first thing that gets printed? 1. Well, then 2, then 3, then 4, then 5. Predict here, what's the last value going to that it's going to be printed? 10? Let's find out. Let's walk through and find out why. 9 got printed. I is now 9. 9 is strictly less than 10? Yes. So we execute the loop one more time. 9 becomes 10. 10 gets printed. We come back up. Is 10 strictly less than 10? No. So it gets, what happens is it prints out now, well, once I recompile it, it prints 1 to 10. I've shifted everything by one iteration by moving this I up to the beginning of the loop. All right? Let me go ahead and move it back down to the end of the loop so that we have our example here. But otherwise, let's see. That's the key. One of the key differences. The initialization occurs before the loop, right? You cannot scope the index variable, that is I, to the loop itself. It must be declared before the loop. So that's a disadvantage in my view of the difference between a for loop and a while loop, that you're not able to scope it down. The increment in this example, our final example here, is placed at the end. However, it doesn't have to be, right? You can place the increment anywhere you want. Beginning, end, or middle somewhere. Right now we're only doing one thing, we're printing something, but if you were doing like 3 or 4 things inside of a loop, you could put it wherever you wanted inside of any one of those things, right? Again, failure to make progress towards that termination condition might result in that infinite loop always printing 0, right? To kill a program, what was it again? Control C. Right? You can also go the other direction. What if I did minus here instead? Right? So I starts out at 0, prints out, but now it's going the opposite direction, right? We're going the opposite direction of where we should be making progress towards it. So it just keeps getting bigger and bigger negative. Now, is this really an infinite loop? There's really no infinite loops because once the universe has reached its heat death, of course, no computers will be operating. But is it really, within our lifetimes here, it will stop. Why? What happens when you get to negative 2.147 billion and change? This one would be underflow because we're going negative, but we wrap back around to positive 2.147 billion, and it will then stop at that point. But we're only up to 2 million, so I'm not waiting around. Again, it is Control C to kill it. Okay. By the way, if you ever accidentally close, I think you, there. I closed my terminal. Oh no, how do I get it back? Well, first of all, you can go ahead and refresh your browser. But there should be, darn it, now I forget. Maybe I'm going to have to do this. Say it again. The 3 dots next to it. There we go. And then, I don't even know what I just did to get rid of it. Up here, there we go. So the 3 lines, good. And then if I misunderstood, I thought the three dots were down below. But there you go, terminal, new terminal. And then you might have to change your directory again back to where you were working, like I'm going to have to. Okay? But that's another way you can kill it. You can go ahead and kill your entire terminal if you want to. That's the nuclear option. Right? Right? So you've got your infinite loops there. So here's a great question. Which one should you use? It is a non-trivial observation that any while loop can be rewritten, not just the 2 that we wrote, any while loop can be rewritten as a for loop and vice versa. I can take any for loop and rewrite it as a while loop. So why do we have 2? You can get by with just one or the other, right? But we like having options, right? Just like in English, you have more than one word that says good, right? Various degrees of good, various different contexts, different slang, right? We like our language to be more flexible, more usable, more readable, right? More, more rich, basically. And so we like our coding languages to do the same thing. It's called syntactic sugar, right? Generally, however, when would you use one over the other? For loops are generally used when you know upfront how many iterations you're going to execute. I want to execute this for 0 up to n minus 1, right? There's your for loop, right? While loops are used when you don't know how many iterations you're going to execute, right? Because you can't just say, oh, I'm going to run this for I being from 0 up to 9, right? I'm going to run this from I up to some number that I don't know yet, right? So what's an example of that? Let's come over here and I will give you an example of that. Right? Let me go ahead and give you int number, right, is equal to 1, 2, 3, 4, 5, 6. To do, write code to determine how many digits are in number. Right? Sometimes when we write code, we use these. Oh, here's a good question. What is that symbol right there? It's not a single quote. It is all the way to the left of your keyboard, right under the tilde at the top. It's called a backtick, right? And that's one way that you can put things into code. That's a markdown way of doing things, but other languages have adopted that. So, for example, this while. How was I doing this while? I backticked it and it made it into a code style in your notes. All right. So, instead of saying quote number, I'll backtick that number. All right. Well, you know immediately because you're a human and you're looking at it and oh, there's 6 there, right? But what if instead of giving this, what if I were to read this in from the command line? A to I of argv sub 1. Right? In other words, when I run this program, sometimes I'll say 1, 2, 3, 4, 5, 6. Other times I'll say 5, 5, 5. Right? In which case the answer would be different. Now it's 3. The computer doesn't know how many digits are there, so we have to write code to determine that. Okay? So ideas here. I'll write down 1, 2, 3, 4, 5, 6 as an example, and then we'll play with this. All right. How would you go about counting the digits? I would start on one end and go, there's 1, there's 2, there's 3, there's 4, there's 5, there's 6. And at the end, I'm at nothing. All right? So yeah, go ahead.
I was going to say that maybe you have some kind of loop that progressively
All right.
divides that by 10.
Oh, okay. Loop.
And then when you get
Divide
down to 0, then
number
stop
by
and actually-
10.
That's enough.
Okay.
That's how many digits there are.
So the proposal here is to divide it by 10. Now, if I were to do this normally, then it would become 1, 2, 3, 4, 5 dot 6. But since this is an integer, what happens to this dot 6? Truncation, and we're down to 1. Make sure, keep on your hand over here, a count, 1 digit. Now divide it by 10 again, but use truncation, 2 digits, right? 3 digits, 4 digits, 5 digits, 6 digits, until you get down to nothing. And what is the numerical value of nothing? 0. Right? So, increment a counter, right? And then loop, okay? There's my outline. What we just did was called whiteboarding, right? And I did it on digitally here, but if I were up at the whiteboard instead, I would probably outline this and then translate it into code. Anytime you're spitballing ideas or with your hack partner and you're talking it out, right? Get up to a whiteboard and start writing out your ideas because that allows you to sort it out, to organize it and say, nope, that's wrong, let's erase it or cross it out. That's right, let's take that over to the second iteration of this thing, right? All right, so I'm obviously going to need a counter. Let's call it what? Num digits. Okay. What should I initialize it to? How many digits have I counted before the loop has started? None, so 0. Right. We'll come back to this loop here in a second, but we're going to have an opening curly bracket and a closing curly bracket. Let me go ahead and put that in there. So now divide the number by 10. I called it what? Number? How do I divide that number by 10? Just like that, right? But is there a shorthand way that we just learned? Divided equals 10. Perfect. Increment a counter. Remember my counter here is num digits. So I'll increment it by 1 is equal to num digits plus 1. Again, is there a shorthand? Plus plus. Or plus equals 1, but plus plus is even better, right? By the way, the increment counters and these things are supported by the vast majority of programming languages. The one exception would be this one is not supported by Python. Bad Python. Yeah.
Plus plus.
The plus plus is not supported by Python.
So do these other um, functions, like the basic ones, multiplication and division, stuff like that,
Mm-hmm.
can you go, you probably can't go divide because that has to do with comments, but.
Yeah, then it's comments. I say what?
Minus?
Yeah, you could go, well, I mean, you could go minus, and then you're decrementing it by 10.
Okay.
Right.
But you can't do it like a plus signs where you just have two plus signs.
No, no, no. That's one, and that's for one only. The value one only. All right, divide, there we go. All right. Clean up your cruft. Once you've done that, great. All right. Now, what about my loop here? Right. If I were to write this as a for loop, for int I equals 0, I is less than the number of digits in number, I plus plus. Well, how many, that's what we're trying to compute. If I knew that up front, then yeah, I would be shopping for a for loop because you know how many iterations up front that you're going to execute. I don't know that, right? So I'm going to go ahead and transform this into instead a while loop, right? Now, what's my condition here? Remember the example that we had on our whiteboard here for 1, 4, 5, 6. We got rid of that, got rid of that, got rid of that, got rid of that until we got down to nothing, which is 0. Number is let's go with that first. All right. So while it's 0, continue with the loop. That would be the termination condition. If it's 0, stop the loop. So all you have to do is not 0. There you go. Okay. GCC this. And let's run it with, I don't know, 1, 2, 3, 4, 5, 6, right? What's our expected output on this? 6. Well, we don't have any output, so let's add that now. Printf, %d has %d digits in it. And the line. And it was the number and then num digits. Okay? Still some bugs. We're going to figure it out and fix it here in a second. But my expected output would be 1, 2, 3, 4, 5, 6 has 6 digits. Okay? The 6 is correct, but the 0 is not. Why?
Because you're changing the number
Yep.
when you divide it by 10.
You're changing the number when you divide it by 10. Right? So if you want the original number, then give yourself some more variables. Int original number is equal to number. Right? And then you can go ahead and change number all you want, and the original is never actually touched down here. So instead of printing out number, I'll print out the original number. There we go. There. Here's a trick. I never want this to change. So I can make it into a const. Right? Now, GCC. I never changed it. In GCC, if I had tried to change it, say original number divided by equals 10, right? Just screw it up entirely. It's going to be error. That's a read-only variable, a constant. Your attempts to change it on line 17 are not going to fly. Error. Right? So, if you need to make something const, then make it const. Let's go ahead and test it. Okay, yes, it still works. What else should I test? 7 digits? That works. What about 4, 4, 4, 4, 4, 4, 4, 4? How many was that? 8. So, did it break if I was using something other than 1, 2, 3, 4, 5, 6? No. Okay. What else should I test? Let's test something small. 44. Okay. 2 digits. Let's test something really small. 4. Okay. What else should I test? Okay. Remember in math, what happens at zero with a lot of functions? Right? 1 over x. Or a sine x over x or something like that, right? It blows up, weird things happen at 0. Those are called corner cases or edge cases, right? And we need to test for those, right? Is this code going to work for 0? It runs, but is that a correct answer? There are no digits in 0. I'd count 0 as 1 digit. So this code is not going to work for that one corner case, that one exceptional case. Let's write some code that does work for it. If number is equal to 0, then we can say printf 0 has 1 digit in it. Right. There. Do I want to continue with the rest of the program if I already know that answer?
No.
Nope. So let's go ahead and exit with a 0 error code. We'll get to error codes eventually, but 0 means No problem. There were 0 errors. All right. Let's go ahead and see if it works now. All right. Hey, that works for that one. Did I break anything? I need to go back. If I'm being a good software engineer, just a good software developer here, whatever, a computer scientist, whatever we want to call ourselves, right? I would have to go back and test every single thing that I just tested. Yeah, that still works. Yep, that still works. Yep, or 7, 8. Yeah, that still works, right? All those 4s. 4, 4, 4, 4, 4, 4, 4, 4. Yep, that still works. And does 0 still work? Yes. Right? That's called ad hoc testing. Right? And it's what everybody does in the beginning. It's what even professionals do as a sanity check. I write a little bit of code. I test it with one input to see if it works, or at least it compiles, right? And then I can move on. It is not the way to live your life as a software developer, right? Making a change, going back and doing 50 different manual tests, that's not a way to live. Instead, you should try to automate those tests, right? You could write a test up here for each one of these. Here's the expected, here's the input, here's the expected output, and here's the actual output. Does the expected output match the actual output? If yes, then great, you score a point. That test case passed. You're going to be doing this in your lab tomorrow. You're going to be writing a function that will determine if it's a leap year or not. Then we give you a bunch of boilerplate code that tests for, like, is 2000 a leap year? Yes, it is. So if your function returns false that it was not a leap year, then it's wrong, right? And we would say, okay, that test does not pass. But we write code to do that. So all you have to do is cut and paste that code for different test cases. Then you only have to run the program once. You make a change, fine, recompile, run that program again. It automates this entire process for you. Later on, we'll be doing formal unit testing where we don't even write that code. Instead, we have input, expected output, framework, you take care of it for us. The framework will be CMACA. All that boilerplate code, we won't even write that. Yeah?
No, I was just curious, since you mentioned leap year.
Mm-hmm.
Or is it going to be like, because technically 1700, 1800, and 1900 were not leap years.
By the rules, they'll be leap years according to the Gregorian calendar. Once the Gregorian calendar was established, all previous years were now leap years. Gregorian calendar, like 1000 AD or something like that. I'm not sure. It's a pretty old calendar. Some calendar systems, the old Roman calendars only had 10 months, right? Then they added 2 because Julius and July and Augustus, August, right? So calendars do change, but once they change, then it changes all past history too. Yeah.
What about the weird, like, century rules or whatever, where, like, every other...
That's out of scope. Yeah, you add like a leap second or something like that.
I think you skip a leap.
Oh no, that loop is there. That exception is there. Every 400 years, even though it should be a leap year, it's not, because the orbit around the sun is 365.24 and then change days, and that 0.24 that contributes to every 4 years being a leap year. But then every 100 years we take off because of that 0.01. But then every 400 years we don't take off because of all the other numbers in there, right? So yeah, but there is also like a cosmic like leap second or something like that, where every 1,000 years or something we have to adjust our clocks or something. Right? I forget what it is. Maybe it's every 100 years or something. There's an extra second there. Right? But in any case, what else should I test here to make absolutely sure? All right. -1, 2, 3, 4. How many digits are there? 4. Good. Now it works because you immediately jump to the correct solution of it's not equal to 0. If we instead had said, as long as it is greater than 0, we would have been making the assumption that it's always going to be positive. Right? And so you're always decrementing here. But what happens now if I had made that mistake? Oops. Come on. Well, oops, no, duh. Greater than 0. Sorry. There we go. It has 0 digits in it. Why? Because number is already -1,234. this loop never gets executed, and therefore, what's in num digits? Well, whatever we started it out with. Right? So let me go ahead and reframe that as not equals. And guess what? We're done. So take out your to-do. Right? To-dos are only there to remind yourself of what you need to do. Once you have done it, take it out. It's cruft. Okay? All right, so I'll make sure that you have this. No, I just want the snippet. I'll make sure that you have this in the notes that will be posted later tonight. And then we'll continue on loops on Wednesday. Some things that you should be aware of, sorry, before we go, are on Thursday there is a School of Computing only involvement fair. It's on Thursday, and I think that it's in Shore, but don't quote me. You can see the posters or consult Bits and Bytes. And like the UNL Game Dev Club will be there. Some nonprofit Initialize will be there. The Coding Club will be there, etc. Friday at 4 p.m. So meet us by Shore, and we'll go out for a 5K, 6-minute 5K, 6 minute per K 5K. Right. So it's not going to be fast.